time. Okay. All right. So I think it's recording. Everything is good. So I'm just going to um, go back to that simulation. Okay. And see how it goes. All right. There's no sponsor here. All right. Oh, that's the wrong one. This is the one. There you go. All right. So now I hope you sort of like play around with this a little bit, and then you understand how this thing is. It's explaining the standing waves in the tube. Okay, and what we are going to take a look at first. So it will be related to what we have is like the tube that has open ends. Okay, so both ends are open. And so now I think we understand it that you can send in the sound or you can generate the sound or whatever at like multiple frequency or whatever. But the only frequency that is going to give you like a dominant sound or dominant frequencies that's going to come out of it is going to be the one that actually matches the boundary conditions. And what is the boundary conditions for this? It is the big oscillation at both ends. And we named these antinodes. All right. So this is the locations that the molecules of airs can actually going back and forth the maximum. Okay. So let me show the original wave. Here we go. So you pretty much generate a sound in there. And every time that sound try to go from one to the other, one mean inside the tube and try to go outside the tube, there'll be a partial reflection going on. Okay. And this reflection of waves, it's going to interfere with the incoming waves. And that is the condition that we studied last time when we have two waves that look exactly the same, same wavelength, same frequency, and running in the opposite direction and meet, they are going to interfere. But then the bottom figure over there, it's showing what is the result of this interference. You can see it, it's not going to have an oscillation that's like, it's not big. The oscillation is not good. So that means this wavelength over here, if it's going to travel inside this tube, the outcome of this one is not going to be that great. You see what I'm saying here? The outcome is the bottom animation there. Okay, cool. Kind of get the idea. All right, and just want to make sure that the reflection will happen multiple times, and that's what I like about this simulation here. So there are actually the second reflection, the third reflection, the fourth reflection, on and so on and so forth. That's because, I mean, every time that sound try to leaks from the tube to the open air, it will have a partial of that sound sort of reflected back. So this thing will happen multiple times. All right. So you have to combine all those stuff. But the combination is so simple, it's just superposition principle. So it means you just add them all. So the bottom tube figure over there came from actually they have to add like super like multiple waves in there, and that's the resultant wave at the bottom. You guys with me so far? So that means at this particular wavelength, it doesn't it doesn't work much, right? You're not gonna hear a loud sound coming out of this tube at this wavelength or this frequency. Okay, got the idea? All right, so once you know this, I think I can just ignore those multiple reflections. I can just sort of focus on the main two, just the first reflection, and get the interference from the opposite traveling waves, and then what's the outcome. That's good enough, all right? Because the multiple reflection will just doesn't really contribute much anymore. So it's usually the textbook will only focus on the first two. That's why. All right. But anyway, what you see over here is, if you look at this portion over here, see that the wavelength that I picked turns out to be 1.15 lambda. So the number is not so great. So what I'm trying to do is I'm trying to adjust the wavelength to make it sort of like some multiple value of the lambda and see how it goes. So what I'm going to do is I'm just going to adjust this to make like a good round number. Let's pick like 1. Okay. Oh, there you go. Oh, there you go. 1. Oh, not there. Okay, here we go. That's pretty close. 1. There you go. All right, close enough. All right, so let's say if I pick the wavelength to match exactly the length of the tube, this is the case, right? I'm supposed to do better. Oh, actually, I can just type in 5. The number is good. So I just type 5. There you go. All right. So I match exactly the length of the tube. And let's run this one and see how it goes. Bam. You see this? So that means this wavelength seems to work. Because if you look at the bottom tube, that is a resultant, that's the total combinations of everything. See, the oscillation of the wave is huge. The amplitude of the oscillation is huge. And then you have to understand one more thing, just want to make sure. This is just a representation of things that is oscillating in terms of like a displacement of the air molecules, right? Because everyone understands that air is a longitudinal wave. So in actuality, the air molecule is supposed to vibrate in the horizontal directions. All right. So I hope you understand what it is. All right. But what we see over here is just like sort of like portraying like the displacements that's going on that horizontal oscillations. Okay. But the whole point over here is, as you can see, the vibration is like, it's great. It's good. Right. This is like the biggest oscillation that you will get. Okay. So that's what it is. That means at this particular wavelength, it works so well. And that's what we call, this is the standing wave. The reason it's standing wave is because if you look at some portion of this one, I don't think I can annotate on this. But anyway, what you can see is at I'll write it down at some point. But what we have over here is, if you look at this one very quickly at the bottom too, this thing is going to oscillate up and down, up and down, up and down, up and down, right? So fast. That's what you saw in the slide or in the textbook. That's what they gave you, this figure over here. So you have to understand now, I mean, the actual wave cannot be like in a loop like this, right? It doesn't make sense, right? It's just like a single, I mean, it's going to be a single line to represent a wave. But the reason that they try to put it in the loop like this, because it's oscillate up and down quickly. So you can just sort of like use this illustration to represent the standing wave. And the point that I was trying to mark on there is just this point right here and this point right there. So these are the 2 points that doesn't move. As you can see, it's always fixed. The molecules of air at that particular position will have no displacement. It always stays at 0. And everything else just oscillate crazily around it. That's fine, oscillating. But at the red dots, no movement. Hence the name standing wave. Cool?
Okay.
Okay. All right. So that's what it is. So that means now you can pretty much like have multiple conditions that eventually will match and eventually generate a very good vibration or very good oscillation inside the tube. So if you go back and play around with this, then there should be some other wavelength that you will be able to play with this. And then I can try some multiple numbers. Maybe let me try like 1.5 and see how it goes. If I can do that. All right. Okay, let's do a good number there. 1.5, close enough. All right, so that means now the length of the tube is 1.5 times the lambda. Let's see how it goes. Oh, that's pretty good. It's pretty good. You can see that the oscillation is pretty much maxed out the whole height of the tube. I mean, that's just a representation, but at least that gives you the scale that, oh, this is a good vibration going on inside the tube. So this is going to be another condition that works. Does that make sense? And if you think of this one as like a fast movement, fast animation, what you are going to generate is going to look something like the next one over here. See, it makes sense? All right, so when the things move up and down quickly, then you can snapshot and then sort of take a look at the picture and it will look like this. Cool. All right. So I hope that give you the whole sort of like story of how can you generate a standing wave. Okay. It came from the reflection, and then the reflection give you 2 waves that running in the opposite direction and then they interfere. But because you need to match the perfect condition of the length of the tube somehow, to make the resultant waves oscillate at the maximum possible value. At that particular point of, I mean, at that particular conditions or the wavelength that you pick, you are creating standing waves in the tube. Cool. All right. So let me go maybe like 0.5. So this is going to be like a long wavelength here. If I can do it. Nope, it's not. Okay. I have to adjust the tube a little bit. There you go. All right. So let me adjust the two. There you go. All right. So there's another possibility there. Just want to play around with the numbers. Okay. So if I can adjust the length of the tube and the wavelength to make it 0.5 and run, will that work? Yeah, it looks good. See? All right. So in the bottom curve, you get a very good like maximum oscillation there. So that's the whole thing. All right. So this represents, see, you if you imagine this to go up and down quickly, this will generate the first figure up top. See? Done. All right. So this is a recap of what we can play around with that simulation. Now here comes the conclusion. So in reality, you don't need to do this summation of the waves. You don't have to do like psi plus psi equal to 2 psi cosine A, blah, blah, blah. Here, all you need to do is just trying to match the boundary conditions. You guys with me now? When I said match the boundary condition, this is exactly what we discussed last time. Because this is this is like a both open ends tubes over here. So we assume that at the ends of the tubes, the air should be able to oscillate at the maximum possible value, or we named it the antinode, the location where the displacements can happen at the maximum. I mean, it can oscillate as crazy as it wants. So all you have to do is just trying to draw this diagram and do whatever you can just to eventually start from the antinode and end at the antinode. Does that make sense? And to get from antinode to antinode, definitely you're going to have you have to go through a node. A node means it's the point where there's no displacements whatsoever in the medium. Okay, so it's just like playing games now. And I'm going to show you how I can do this one more time. We did this last time, but I hope this time you understand more. So let's say I want to start from antinode. I want to end at the antinode. So the easiest type of waves that I can do is just start from antinode and go down here to another maximum here. And that's why you end up with this first figure in the top right there. With me? Another possibility is you just put one more twist to it, but then eventually you get back to the place where you have the maximum displacement. That's you get the second figure over there. Or you can put extra twist there. There you go. There. And then you get the third figure. And then you can keep having fun with this. You put extra one more twist to it. There you go. You got that? All right. So this is how easy it is for you to be able to evaluate or try to find the value of the lambda of the wave inside this tube. Because what you want to just do next is, Ajahn, if I know the length of the tube and I know the shape of the curve of the wave is actually has to you just look at the single one of them. You don't need to look at the multiple of this. All right, that is one at one particular time. It's going to look like a blue curve right there. But everyone knows when you look at the blue curve there, when you start from here, you end up at exact same spots that look alike but adjacent to each other. That is one lambda of the wave. With me, guys? Does that make sense? All right. So what I'm saying over here is now you can see that you can just count on this. One, and you do, oh, that's two. Or maybe scaling is bad. That's my bad. But anyway, that's my point. The point is this particular configuration over here will give you say, hey, 2 lambda is just the length of the tube. And that's it. You're done. The lambda that is half the tube's length will give you one standing wave. Cool? All right. Oh, there's a question coming in. So what comes into the tube will go out exactly the same. What comes into the tube will go out. It will go out in the form of the interference. And how is there a reflection when both ends are open? Isn't the wave supposed to just pass through? Okay, here's the cool thing about this one. We will learn more today as well, maybe the second half of this lecture. But what we have over here is waves. Every time that the medium have different properties. Yeah, different properties. What I'm saying different property means, for example, maybe the medium, the air, have low density and the other portion of the air has a higher density. The wave will behave differently. So that's why what I'm saying is the air inside the tube and the air outside the tube will have different physical parameters. So the wave will behave differently inside and outside the tube. Does that make sense? All right. And you will see more and more when we learn more about waves. Every time that waves try to go from one place to the other place that has different physical parameters, they will always transmit and reflect at the same time. Does that make sense? So it's not going to be like 100% getting through. There will be, of course, majority of this one will go through, but there will be a partial part of the waves always get reflection back. And that is the one that eventually gets sent back to the tube and do the interference. Does that help? All right, maybe thinking about sound is kind of like a little tough, but you will see today that if you look at other kind of waves, which is light that we're going to discuss after this topic here, you will see even sort of like clearer when the light travel from one to the other mediums, then you get some reflection part, some part get reflected, some parts get transmitted. So the sum will come out. Yeah, the sum, because there are two directions, but if you sum those two, the one that go through and the one that get reflected back, you still get the original. Yeah, everything has to conserve. You cannot lose the wave, or the waves is waves. So it's physical stuff. So the energy or whatever you want to analyze about the waves stays fixed, but they just got separated, split out. Okay, does that make sense? All right, okay. So I think I have one more explanation that, sort of like some demonstration. I'll show you how it's, and I will help you understand more. So what I'm going to do is this. Let me finish this analysis of the wavelength in the tube first, and then I will show you the demonstration that I hope it will get connections to what we are discussing right now. I hope. All right, but anyway, so this is how easy it is for you to determine the wavelength inside a tube. Oh, did I answer your question? Okay. Yeah. About the wave getting out and getting in, outside, inside the tube. Yeah. Okay. All right. Okay. So now, once you know how to do it, let me ask you this. Well, hey guys, give me the wavelength of the first figure over here. What should be the wavelength of the first figure here? Well, Ajahn, that's not bad, because if you try to trace this curve right here, oh, that is only halfway to the completion of the full waves. So what you can conclude about this one is, oh, Ajahn, for the first one, it's only half a lambda, right? Because that's what you get, half a lambda over here. It's the length of the tube. And hence here, see that? That's why they say the lambda is twice the length of the tube. Once you get the lambda, you can figure out the frequency by using a simple V equal to F lambda. So F equal to V over lambda. Take the lambda, which is 2L, plug it in there. You can determine the frequency as well. So it depends on what you want to talk about. You can talk about the wavelength, or you want to talk about the frequency. That is fine. Okay, now move on to the next. Here we go. All right, try to practice this one more time. See? That's full wavelength. You come back to the original, the shape of the wave come back to the original shape. So you start from here, you end up there. That's one complete cycle. So in this one, you say, oh, one wavelength is the length of the tube exactly. That's right there. And if you want to find frequency, just take V divided by that lambda, which is L, and that's done. V over L. So you see how easy it is to determine the wavelength in the tube. Here we go. If you twist one more, so you say, well, John, that's fine. So this is one wavelength and a half. See that? It's 1.5 wavelength over here. So it's 1.5 lambda equal to the length of the tube. Okay, so that means the lambda is just, you can write 1.5 to be 3 half. So it's going to be 2 L over 3. And that's what it is right here. And if you want to find the frequency, just flip it down, divide out the V, and then you get the frequency. Done. Cool. Isn't that nice? Okay, so that's what it is. That's how easy it is for you to determine the wavelength or frequency in a standing wave. So that's, I said, final conclusion is simple. Understanding this one, it's kind of tough because there's funny business going on inside the tube for you to understand. All right, now let's look at terminology. This is also throwing some confusion into the mix here. what you saw over here, if you figure out the frequency, and because this is the lowest frequency that you can get, or the highest wavelength that you are going to, it's available for these two, you're going to call this the fundamental frequency. Whoa. All right. So this is a fundamental frequency. Okay. And because this is the first frequency that you're going to be able to hear from this one, is the lowest frequency possible, you call it the first harmonic. All right, this one sounds like, you know, music theory a little bit, I guess. I don't know. All right, now move on to the next. All right, the next available frequency turns out to be twice the original fundamental frequency, because you already matched that one. The fundamental frequency is V over 2L, and this one is V over L, or which means you can think of it like 2 over 2. So it's twice the fundamental. So that's why what you're going to name this one, you're going to say this is a second harmonic, because it's twice the frequency of the fundamental. Does that make sense? All right. Now, if you move on to the next, then you can say, oh, Ajahn, for the next one, it's 3V over 2L. V over 2L is just the fundamental frequency, right? So that means the third available frequency is triple the frequency of the fundamental. So you're going to name this one the third harmonic, on and on and on. So now you understand the harmonic. It just means that if you say the first harmonic, that was just the fundamental frequency. And then the next available frequency, it just depends on how many times in comparison to the fundamental frequency. So if it's twice as big, you call it the second harmonic. If it's 3 times as big, then you call it the third harmonic, on and on and on. Okay, cool?
Okay.
Right. However, there's another word. So many things going on here, because the fundamental frequency is there, but then the second one that is available is just one step from that fundamental. Sometimes they refer to this one as the first overtone. Is that confusing there? Yeah. So it's the next tone that is available. So for the both ends open tube like this, the first overtone is the second harmonic. You see what I'm saying here? And the third harmonic is going to be your second overtone. There you go. Okay.
Okay.
All right. It will be clearer. What I'm saying over here is just like, Ajahn, why do you have to sort of like come up with so many terminologies and, you know, agreement in the names, all this stuff? Look at the case that now you should be able to, you know, figure out what is going on if you have one open and one closed end tube. Okay, one closed end, one end closed, two. All right, let's take a look at this one. Skip to the other here. Now, I hope you understand how it works now. So if you have an air column or the tube that has one open, one closed ends, how can you imagine what will be the available frequency that is going to give you standing waves coming out of it? So the key is just match the boundary conditions. Your boundary condition over here is because one end is open, that open end is supposed to be antinode. Okay, the air molecule vibrate the maximum. And because the other end is already a wall, so the air molecule that's stuck on the wall shouldn't be able to move at all. So that should correspond to the node. Does that make sense? And the rest, just playing games. So you have 1, 2, okay, let's play together here. And the key is just starting from the antinode down to the node. What would be the first thing that's possible? You just, yeah, there you go. There you go. Yeah, you start from the antinode and then you end at the node right here. That's the node. So this is good. And because when you look at this one, it's just like, Ajahn, I can see now, if you trace this curve, oh, it's just 1/4, because you have to go all the way there and all the way up and up again. So actually what you're seeing over here is just 1/4 of a lambda, right? That you're seeing inside the tube. So that means 1/4 of the lambda is the length of the tube, or the lambda is 4 times the length. Cool. All right. And now you play the next game. Okay. Okay. Let me try it again. Oh, it's too far. So what I can do next is, Ajahn, I can put one more twist to it. but then I have to end at the node. One more twist, but I have to end at the node. So I'm still constrained to our conditions where the open ends has the antinodes, the closed ends has a node. And now when you try to look at this curve, Ajahn, this is, oh, it's almost one complete lambda, but it's missing a quarter of a piece. You guys with me? So over here, what you're seeing over here is like, oh, Ajahn, it's only 3/4 of the lambda that is the length of the tube. So in this case, lambda is 4L/3. Cool.
Okay.
Yeah. So the closed end has to be a node and the open has to be an exactly correct. Very good.
Okay.
Perfect. That's what we want. We just have to be able to match the boundary of the ends conditions. And the rest just fit those conditions. You can squeeze in whatever type of the wave as long as it's fit these conditions, it's going to generate a standing waves in there. Okay, let's do one more, shall we? Okay, all right. So another thing that you can do about that, let's squeeze in one more twist, shall we? Well, yeah, I can do that. I can do wham, wham, but I have to stop at the node. Wham, wham. There you go. So that's the third figure over there. And then what you have to do is just like, okay, this is, that's one wavelength. And then you have a quarter of it extra with me. All right. So in this case, it's already one wavelength and a quarter. Cool. So what you have over here is it's going to be a quarter, quarter. So you're going to have 5 lambda over 4 of the lambda, right? Equal to the length of the tube. And hence, there we go. The wavelength is going to be 4L/5, on and on and on. So this is how you evaluate the wavelength in the one open, one ends air columns or tube right there. Cool.
Okay.
Not too bad. I know. I mean, the end result is super easy. It's like playing games. But the underlying physics principle is like you need superposition principle and you get the interference of waves in there. Is there a case where the tube has both ends closed? That's kind of weird for the sound, but actually we already discussed that both ends closed using a string. Remember this? Here we go on the left. That's correspond to the both ends closed. But if you really want to do it, I think you can. If you are inside a tube that has both ends closed, and then you have a speaker in there, like you might be in like a tunnel, for example, where both ends closed, and then you have a speaker in there, and you send out the sound, multiple frequency, there will be only some frequency left in that it's get bouncing back and forth and give you the highest or the maximum sound level to your ears. Yes, so it's possible to have both ends closed, but that one is easier to sort of visualize using strings. Yeah, because strings, when you fix both ends, that's guaranteed that you're gonna always have the nodes at both ends. Cool. So we pretty much complete all 3 cases. Yeah, open tubes. I mean, open at both end tubes, one open, one closed tube, and both end closed. Or I mean, a string. Yeah. Cool. All right, but you use the same techniques. So let me just do this for you guys here. For example, over here, you're, oh, Dan, this is half a wavelength. So if you're particularly interested in this one, you say, okay, lambda over 2 is the length of the string or length of the tube. And then if you go into the next one, well, Dan, this is one complete wavelength. So that's good. The next one is going to be lambda is exactly the length of the tube, on and on and on. All right, cool. Now come back to our naming scheme. Once again, now you understand all 3 figures on the left, and you know how to figure out the wavelength, which is good, right? Once you know the wavelength, you will be able to figure out the frequency. You just take the velocity divided by the wavelength, you get the frequency, right? This is your fundamental frequency or the first harmonic. You guys cool with this? Now you understand this, right? Now move on to the next. We already figured out that the lambda is 3L/3. Now, if you figure out the frequency, it's going to be 3 times the fundamental. See it now?
Okay.
So that means this is triple the frequency of the fundamental frequency. So that's why we name this one the third harmonic, because it's triple 3 times. Okay. And of course, now you can imagine the bottom one, because we can see that this bottom one is 5 times the fundamental frequency, or that means it's 5 times the first harmonic. So this one's supposed to be named fifth harmonic. I think this is the name of the band or something, right? The fifth harmonic. But anyway, that's what it is. Okay. And in terms of the overtone, now you can see this is your first overtone for the one open, one closed tubes. One open ends, one closed ends tube over here. And that means in this particular setting, first overtone is the third harmonic. And this fifth harmonic is going to be your second overtone. Isn't that? I hope this is not confusing anymore. Okay. So harmonic, strictly speaking about the frequency, comparison to the fundamental frequency. Overtone is just the listing, starting from the fundamental frequency. The next available frequency is going to be the first overtone. The next available frequency will be second overtone, on and on and on. Okay. The overtone doesn't care what is the relative frequency with respect to the fundamental. Does that make sense now? Okay.
Okay.
And that is pretty much. And I hope by completing this, it is done for this topics over here. I know I spend, usually back in the day, I don't teach much of this at all. As you can see, the number of slides is so small. However, this is the one that people get confused the most because they just don't know what is going on. Plus, the textbook give you this sort of like the drawing over here, which is misleading somehow because actual waves doesn't do a loop, right? And the analysis somehow they're stuck sort of, I don't know it's stuck or not, but they try to saying that, hey, once you understand this thing, let's look at the loop, which the loop doesn't really come out in sound. I mean, what is the loop in the sound? But if in a string, okay, that makes sense because you might be able to see this kind of loop in like a guitar when you plug the string and then sort of the guitar string just oscillate back and forth. It seems to form a loop so you can see it. But in sound, there's no loop. All right. So that's why I try to make sure that you understand I think this is just like a visualization tools that allow you to analyze this one a little bit easier. Okay. Because the sounds, the air molecules and everything, they are longitudinal waves. So they're just oscillating back and forth. They don't do the loop just like in a string, but the analysis are exactly the same. Okay. It's just like I always say, the good thing is longitudinal or transverse waves, you use the same sinusoidal waves, sinusoidal functions to analyze anyway. So this is sort of like the showcase of what I mean by that. Okay. All right. So with that, if you really want a link to a loop, just in case you read the textbook and all this stuff or some other book, then they will try to show you this, like, okay, every time that you can see a loop like this, one single loop is always equivalent to, you can see now, but then of course, one loop is just halfway, okay, it's just halfway to a complete loop. So that's why all the time, if you want to talk in terms of loop, one loop will be equivalent to half a wavelength, if you like. Okay, so it depends on your preference. If you want to count the loop, that is fine. For example, but I love to count the loop. Let's count it. So like, for example, like this one loop, 2 loop, and a half. So that's good. So in this particular case, it's going to be 2.5 loop. And it's 2.5 loop is just one loop is half a lambda. So you're going to get 5/4 lambda anyway. Same thing. All right. That's not going to be anything different there. So you can count that there are 5 lambda over 4 that is equal to the length of the tube. And then you get to the same conclusion anyway. Okay.
Okay.
All right. So your choice. Okay, you can look at the wavelength directly, or you can look at the number of loop by knowing that any loop will be equivalent to half a wavelength right there. All right, so any questions, guys? All right, so if not, then there are like a simple question that I want you to try. Let's try this one. Section of drainage covered 1.23 meter in length makes a howling noise when the wind blows across its open ends. So that's usually happens when wind blows into some tube, then it generates some, howling sound. No, right. Determine the frequency of the first three harmonics of this culvert if it is cylindrical in shape and open at both ends. So think of it like an open end tubes, that's all. All right, and the velocity of the sound is given, and the length of the tube is also given. Give me the first three harmonics. All right, guys, go for it. All right, I'll prepare some demonstration for you guys, so I hope you understand more. Give me 1 second here. All right, while you working on this problem. Got that one? Already. So the calculation, I don't think is that bad. Okay, because now you assume the open at both ends tube. So now you understand that to be able to fit the standing wave in there, you just have to do this. That's the first case, and then they want first three harmonic, right? So actually, if you go back to the previous page, it already listed all possible numbers in there for you. So you should be able to just copy those formula and just plug it in. So you're done. But I just want you to be, oh, you got numbers for me. Thank you. All right. Yeah. You just say, okay, John, we already got this result saying that it's actually is you just copy this. You know that the first wavelength is going to be 2L, or if you want to jump right into the frequency, it's going to be V over 2L, 2V over 2L, 3V over 3L. So let's make it very simple. So you say, okay, the first frequency is going to be V over 2L. By understanding that, oh, because the wavelength is going to be twice the length of the tube. And that's it. The velocity is given and the length of the tube is given. And then you're done. Come out as the units in hertz. Thank you for the numbers. All right. I trust you guys. That's the answer. And the good thing is, once you get the first fundamental frequency calculated, you don't have to do anything anymore, because now you know that it's the open end tubes. The next one is going to be twice as big. And the third one is going to be triples of that. And then you're done. Like your friend just writing there. Is that right? Is it twice and 3 times? Yeah, I hope so. Yeah, perfect. Very good. That is it.
Okay.
See? So the problem of this topic, I mean, at the end, the problem is going to be super simple. Okay, try again. One more. Speed of sound is 340. It's up to you. And because this problem, they just give you 343, just use 343. But if it's not given, you can use 340. That's up to you. Yeah, that's all good. I mean, it's just approximate value anyway, right? Depends on the temperature of the air, the condition of the air at that point, but it's somewhere around 340, 350, anything's around that. And the next example, just say, hey, what are the 3 lowest natural frequency of the culvert if it's blocked at one end? So it's mean you just change the condition and everything turns into one open, one closed. That's it. Okay. And now you understand that, okay, John, in the first wavelength over here, the frequency in the fundamental is going to be V over 4L. Okay, because now we know that, okay, the wavelength is supposed to be 4 times the length of the tube. And now you know that the first overtone, the next available frequency is going to be triple that. It's only the odd harmonic. And the third overtone is going to be 5 times that original. So that's it. That's how simple it is for you to carry out this calculation there. All right, but I hope you having fundamental understanding of what standing wave is about. Okay. However, I mean, to be realistic, and I think you guys have seen this. I don't know if you have seen or not, but you have to experience this. Okay. I have a bottle of water right here. And every time that you try to fill up a water in the bottle, you will be able to observe a sound, right? Coming out of it, right? Oh, that's a question first. Isn't third overtone the 7th? Third overtone. Yeah, third overtone is going to be 7th, correct. But right now, the first overtone is just here. This is the first overtone. So what we want up to is just only second overtone, because they want us to list 3, right? The first 3 frequency. So we just stop at second overtone. Yeah, but the next one will be 7th, correct. Okay, come back to this. So in general, when you want to fill up a water, fill up a bottle with the water, you will always hear a sound, right? It's like, does that make sense? Right? All the time, it's like, that's what it is. The frequency of the sound that coming out of it, it's higher in pitch, or the frequency. And I think now you understand why it is so. Because look at the bottle of water. At first, you don't have anything yet. So whenever you generate the sound inside a bottle, the wavelength, it's gonna be this big. With me, guys? But then when you fill up this bottle with water, then you're gonna sort of get the level of water up and up and up, right? Up and up and up and up. So this is exactly one open and one closed end tube. So that means the wavelength that's gonna fit in there is gonna get shorter and shorter the more water is in the bottle. Does that make sense? Let's get shorter and shorter and shorter and shorter. That is the reason why you're hearing the all right. And every time that you're going to try to generate any sound, it's going to depend on whatever the length of the air column that you have in there. You're going to hear only one, well, it's not exactly one sound, but you will hear the dominant frequency out of it. I'll show you. This is the only bottle that I have that is not big enough. All right, here we go. So if I blow the top of this bottle, see, you will hear only like the main single frequency out of it. I don't know, can you hear that? And then if I drink this one a little bit, so that means I generate the longer or deeper air column in here, the frequency will be dropping. The frequency will go to a lower frequency. So remember this frequency? Okay. And I blow it again. See that? The frequency is dropping. And if I drink it again, now you have a larger, I mean, sort of like a deeper air column here. It's even lower. See, that's what it is. So when you fill up the bottle, then the sound will go in reverse. It's go from low frequency to higher. That's because you reduce the length of the air column in the bottle. Does that make sense? I don't know, is this a good demonstration or not, but I hope it's very relatable to everyday's experience there. All right, there is another thing that you can also try to do at home if you like. You can bring a straw if you want, and then you just maybe you just clip the end a little bit just to make it like go crazy at one end, and then that will pretty much like that would generate some weird sound coming out of it. All right, so you can just sort of clip the end just to make it like uneven, just to make some vibration in the top of the ends of the straw over here. And what you can do is, while you blowing on it, you just cut the straw to make it shorter. I'm gonna cut it right now. What you expect is you're gonna hear a higher pitch because the column of the air in the straw will be shorter. So here is I don't know, can you hear it? I'm gonna cut it in half right now. Yeah, that. This is gonna be higher in pitch. And then if I keep cutting, this is a bad demonstration there, but you can hear that it's getting higher in pitch with the same explanation. You generate standing wave in a straw where I already flied out. Okay, anyway, all right, in a straw. And then because once you cut down the straw, it's getting shorter and shorter. So the wavelength getting shorter along with it, and the frequency getting higher. So that's why you're hearing a higher tone, higher pitch coming out of it. Cool. All right. I don't know. That is done for my demonstration.
Okay.
All right, guys. I hope this is pretty much closed now this chapter about sound. And this is the last topic about sound that we are going to discuss here. All right. So I think this is a good time to take a break as well. And then we'll come back and move on to the next handout, which is about another kind of waves. It's light. Okay. And then we'll see you after the break. Sounds good? All right, guys. So take care.
Okay.
All right. So we are about to talk about another kind of light. Another kind of wave, which is light wave. Although we are not talking about the aspect of that oscillations anymore. So it means we are not going back to talk about the sinusoidal stuff and things like that anymore. We are going to look at a simple aspect of light, and that makes your life a lot easier. We are going to use the word geometric. So there is like a geometric. Optics is about studying of the light traveling, the direction of light, and all the stuff you use in optics. But then the thing is, in the optics, which is the light business, there are two separate sort of like a subcategories for you to study. One is geometric, that is about we are about to do here, and the other is called physical optics. The physical optics, that was the one that used like sine and cosine and interference, superposition principle that you just saw before with sound. All right, but because I think we already had enough of that, so we are going to look at some aspects of optics that only utilize geometry. So that's why this thing is kind of like nice, because you don't need calculus or even trigonometry. Well, you still need trigonometry, but you don't need like, identities and all the stuff that try to manipulate this and that functions of sine and cosine. So that's why we named it geometry. It's just geometry of light. That's good.
Okay.
All right. So what we are going to study today is just learning about reflection, refraction. These are the two properties of waves. It doesn't have to be light, but once again, for this particular topics, light seems to be easiest for us to relate to. So that's why we're going to study reflection and refraction using light. Okay. And we already understood the interference using sound, because we can hear it when it's constructive, when it's destructive. You can hear it's like a loud sound and the quiet sound consecutively. So that's what happens then. Now we're going to look at the other two properties of waves. It's a reflection, that's you sort of familiar already. And another one that's a very crucial stuff today is refraction. Okay. And we will see what is that. And eventually this will lead you to a very important properties of light. It's a total internal reflection. And believe it or not, you use this one every day. Wow. You'll see what it is. All right. And next time we will then talk about the image formation on and on. All right. That will be next lecture business. Okay. So let's take a look at the reflection, guys. Oh, I'm sorry. Let's take a look at the starting point of this geometric optics, guys. So what we have over here is because we don't care about the internal structure of this wave anymore. Okay. So when I say
Okay.
don't care, I mean, it doesn't mean like we don't don't care, but it just means that we are going to look at how this light travel in space without have to deal with the fluctuation of whatever inside anymore. All right. And actually, we don't even know how to treat that one up to this point yet until you study electric field and magnetic field. So what we care about is just the traveling direction. That's why we are going to use arrows. And of course, we're going to call it rays of light. So that means the laser beam will be the easiest one for you to think of. Every time you shine a laser beam, you have a direct line of light. That is the rays of light. And if you attach an arrows to it to just give the direction of the traveling light, that is your arrow that you're seeing here. It's the same thing, okay? And this one, you know, I mean, if you agree with me for now, you might not know it yet, but because light is a transverse wave, it came from the oscillation of electric and magnetic field. So you can say it's a transverse because the electric and magnetic field actually oscillate up and down. Or maybe something like that. There you go. Oh, just bad. Okay, something like that. All right. And actually, there's a magnetic field as well going opposite to it. It's not opposite, but it's sort of like going in another direction. Oh, that's bad. That is bad. Okay, I try to make it like as close to be real as possible, but that might not work well. There you go. All right, that might work. Something like that. But anyway, the point is it's a transverse wave. So that means whenever you look at the rays of light perpendicular to that direction will give you a wave front, right? The wave front that we already understood back in the day, that if you want to mark a point on there and then just to track that point, I mean, the point that look alike on that wave, you can name those wave front. So this go back to this. Okay, so this is something that you can imagine better using like water's wave. The water's waves seems to be the sort of like portray this scenario a lot better. So if this is like, think of it like a top view over the ocean or anything, that blue straight line, those are the water's wave. Yeah. And now as you send this water's wave into an opening, then something will just leak out like this. Okay, so that's no problem. You have seen this before. But once the opening get closer and closer, now you start to see the spreading out of the wave, right? See? And even closer and even more is smaller, then you can generate like a wave that look like a, you know, come out like in a circular fashion. This is the stuff that you're going to have problem with the geometric optics. What I'm saying over here is if you look at this case or this case, arrow will not help, because if you try to trace a wave, it's coming in here. So this one is still fine. You can use an arrow or rays to represent this traveling direction. But once it's going through the opening, you don't know what to do with this arrow. Is it going to split in three, something like that, or what? I mean, you don't know what it is. So this is what I said. This is the physical part. See? All right. And this property of spreading out of the wave, we have a name for it. We call diffraction. And the good thing is we don't do diffraction in this course. So that's nice.
Okay.
because you want to do diffraction, it just means that we need sine and cosine back again. There's a question, perpendicular. Yes, yes. So perpendicular means you talk about the wave front, right? And the transverse wave. Yeah, very good. Yeah, that's perpendicular. So what we care about in our topics here is just, I don't want to deal with this. No, no, there will be no spreading out. There'll be nothing. We will only care about the light that actually go through something, and you can still represent the traveling direction using that single lines of arrow or the rays, such as like this. For example, you might have a light coming out from a point, and if you want to trace this light, oh, the screen doesn't update. Wait a second here. I think the internet problem, I guess. You guys still hearing me? Okay. Wait. The screen does not move with me. Hello. Okay. No, no movement. All right, I'm back. I think it's reconnect. That's why I thought it's a problem here. All right, give me a second, guys. All right, everything is good. All right, here we go. So what we want here is just, for example, in this scenario here, see? So if you have a light coming out from maybe the tip of some object, the black dot over here, oh, the black dot there, then if you want to follow one particular direction of light, then you can represent it using the ray. For example, ray number 1, light just going straight out to the right, and it might hit something, it might get into something, I don't care, but at least all it does, just changing the direction a little bit, that is allowed, but you can still use the rays to represent the traveling direction. This is good. There's no spreading out, there's nothing, so it's fine. Okay, so this is geometric optics that we are about to do here. Cool. So next, let's start with the easiest one, and then you will see why we only need geometry. It's the reflection. Law of reflection is simple. In one dimension, you already did this with the standing wave or a wave on a string. You just send in a wave, and once it hit the wall, the wave will just reflect back, something like that, right? So this is the reflection, but it's in a single dimension. So that's why it's easy, is only travel left and right. But over here, you can do in like, it's actually 3D now, but the good thing about the reflection is it's always happen on a plane, on a single plane. So that's why actually everything just comes down to only 2D, such as this one, for example. If you have a light incident, so you can name that one an incident ray, hit onto some surface, and of course it will get reflected. You can name that a reflected ray. The rule is very simple. You make a measurement of the incident angle. You name that theta 1 if you like. That is the incident angle. The law of reflection say the reflected ray will make the same angle on the way out. Isn't that easy?
Okay.
All right, so that's how easy it is for you to do that, and everything must be on a plane. There'll be no reflection that coming out of the plane. Plane of what? Every time you want to define a plane, you just have to have some reference as well. And that reference is in here, normal line. Every time you make a measurement, oftentimes actually it doesn't have to be 100%. But in the formula, when they talk about the angle of incident, angle of reflection, whatever, those angles usually measured with respect to normal line. What is the normal line? Is the line that you draw perpendicular to the surface of the material that you're talking about. Okay, so in this case, that's why theta 1 is an angle with respect to the normal line. Theta 1 prime, which is a refracted angle, it's the same thing. So the law of reflection is simple. Okay, and that's just like everyone seems to agree with this. Like, okay, John, it's just coming from, starting from 1D, turn into 2-dimensional, 2D reflection. It's supposed to go like that. And this one look exactly just like when you do mechanic, when you throw a ball into it and it's bounced off the wall like that, it's still the same kind of reflection. It's like elastic collision and all the stuff, and everything just go out like that. Okay, but it's not the same business, but that's what sort of like analogy with the mechanical stuff there. Okay, and the law of reflection happens at a point. So that means you have to consider this reflection like at a point of contact. Okay, so that's give you an idea of what happened if you have like a very smooth surface. So the reflection will happen in the same manner no matter what point on the surface you're looking at. So on the way out, the waves still look very, very good. It doesn't change the formation of these rays on the way out. So that's why what you get over here is we call a specular reflection, and you will feel that this is like a glossy surface. It's kind of like, shiny stuff because everything just come back to your eyes very beautifully. But on the other hand, if the surface is kind of rough, okay, so you still apply this law of reflection locally. At any point of contact, you have law of reflection apply. But because of the surface is rough, the outgoing rays seem to go all over the place. So in this case, you will see as a result, it's going to be like a matte surface. It's kind of like, okay, you don't see your own reflection on there, on and on. So we call this a diffuse deflection. Is it cool? All right. So I think that's something that you can relate to. Okay. And every time that now you understand this law of reflection, even though it's so simple to use, but at least you understand when things shiny and things sort of like dull, or doesn't reflect well, or it looks smooth, sort of like matte finish, like your makeup and all this stuff. You put powder and all this stuff in there just to create the roughness. It's a like microscopic roughness on the surface to make it diffuse the light coming into it. Okay. All right. That's easy part. There's nothing very interesting much, right? Even though that's very crucial properties to study. Next one is the most important one today. It's called refraction. So instead of going reflected back, what happens if you have another kind of medium that still allow light to go through? For example, glass. Everyone knows that light can travel through glass. Okay, so that means if you send a light from the air and it turns out it hits the interface between air and glass, eventually light is going to get into the glass, right? However, because now comes the time that we say, see, the medium of light traveling is changed. This is exactly what you asked before, was like, Ajahn, what happened inside the tube and outside the tube? The air property inside the tube and outside the tube having different properties. So it's just like you going from one medium type to another medium type. Same thing over here now. I think it's clearer in light. Light travel from air to glass. It's changing the medium that it's traveling in. It's going from air. You can think of it as like a vacuum, and then you get into the glass. Does that make sense? Okay. So it turns out the direction of light will not stay the same anymore. And at the point of contact, if you have an incident ray making an angle theta 1 with the normal, always we take angle with respect to normal. Yeah.
Okay.
And we want to come out in the second medium, which is glass. It turns out it will get to another angle, theta 2. And it turns out the theta 1 and theta 2 are related through Snails Law right here, guys. Welcome, Snails Law. The form of the laws looks like this. It's N1 times sine of the angle equal to the N2 times sine of the angle within that second medium. So all you can think of is like the product between the N and the sine of the angle within that medium stay fixed, if you like. But the problem is, what is N, Ajahn? What is the N here? N turns out to be defined as this. Here we go. It's just the ratio between the speed of light in the vacuum, which is, we always know this is the maximum speed attainable in our universe. It's around 3 times 10 to the 8th meter per second, and divided by the speed of light in that medium, guys. Okay. So that's the simple definition of the N. It's just like C over V. C, we reserve this for speed of light in vacuum. And the V, that is the speed of light in that medium. Now here comes the question. What do you think the speed of light will be in glass relative to in air? What do you think? Is it going to be faster or slower? The answer is supposed to be simple, Jambo, because this is the maximum speed, right? So it shouldn't be anything that can move faster. Yeah, in air, it has to be faster than in glass. And especially if air is super thin air, you can think of it as like it's a vacuum. So that will be the quickest, the fastest light can travel, definitely, right? Very good. So the answer is correct. But now, do you know why? That's the question.
No.
Do you know why light travels slower in glass? The thing is, I just have to tell you like a story a little bit because we haven't studied electricity and magnetism just yet. But the thing is, because we said light is electromagnetic wave. Oh, let's try your answer first. It reflects off particle and glass is more dense. That's good. That's very close. Exactly right. So in general, it's the electro and magnetic, right? Electromagnetic. So it's actually turns out to be, it's an interplay between electric field and magnetic field. So the electric field will sort of like create magnetic field generate electric field on and keep going. And that's generate light and it's traveling at the speed of light. But it turns out once you put this light in some medium like glass is made of like, you can make like silicon dioxide or whatever. There will be oxygen molecules in there, silicon molecule in there. There are electrons in the way. So now electric field and magnetic field will interact with those those charged particles inside the medium. So it turns out those charged particles will just, surf the wave, right? And it's sort of like making the interplay between electric field and magnetic field getting tougher because it's sort of like you guys come in the way. It's like electrons in the way, proton is in the way, atoms in the way. So that makes a little bit harder for light to keep going doing that process. So that's why light travels more slowly in other mediums than vacuum. Does that make sense?
Okay.
All right. And as you said, that's true. The denser the material, it's just sort of like rule of thumb is not perfect rule, but tendency goes like this. When you have a denser material, the light tend to move even more slowly because it, so much is in the way. So it's get tougher for light to get through. Yeah. So light reflects when it enters Earth from space. Correct. Yeah, definitely. It has to refract. Actually, it starts refracting from the atmosphere because once it get into the atmospheric region of the Earth, you start to have some, gas molecules running around. So it's not a vacuum anymore. So it will start to refract right away. And I think you come in the right direction here. And this is the reason why you see the skies blue during the day, and it's yellow reddish in the evening because of that. I mean, partially is refraction and there'll be some scattering and all this stuff. Yeah, there's so many things going on. That's the refraction is everywhere pretty much. There's always that. Okay, isn't that cool? Already. So that's what it is. The definition of the N is simple, C over V. We call this N the refractive index or index of refraction, guys. We're going to sort of use this one mainly, index of refraction. Very good. All right, make it simple. And one thing that you have to understand right away, or at least to notice this, N supposed to be larger than or equal than 1 all the time. Does that make sense? Because speed of light in other material never go beyond speed of light in vacuum. So N will never go below 1. N has to be the numbers that larger than 1 all the time. The best that it can do is just N equal to 1, which is speed of light in vacuum. Cool? All right. And I think the reason behind this definition is like, Ajahn, why do you have to define this? Why don't you just use velocity and be done with? I think it's just, we don't like division of numbers that much, I guess. This is my guess. Yeah. We always love multiplying numbers, not dividing numbers. So if you don't define the N, so the formula will look like N sine theta 1 over V, and then there'll be a ratio all the time. I guess. I don't know. Yeah. Or maybe it's just the formulas look nicer, or it's just easier to type back in the day. Okay. All right. So back to our business over here. So now if you want to rearrange this and, well, Ajahn, let's go back to the roots here. You can take the ratio between the sine of the angles. It's going to be the ratio between the refractive index. So sine theta 1 over sine theta 2 is going to be equal to N2 over N1, right? But then by definition, because it's inverse proportional to the N, you can say it's the ratio between the speed of light, and so far so good. Now you say, hey, Ajahn, let's go back to our roots here. V equal to F lambda. So I should be able to write this one as the lambda 1 over lambda 2 as well, correct? And I can write it like this. Does that make sense? Now here comes the question. Why did I leave that F1 over F2 alone, not including in this box right here? What do you think? What do you think, guys? Why don't I put F1 over F2 in this box, but I only keep the lambda 1 over lambda 2? Any clue? Okay, the thing is this, eventually something has to be fixed. It cannot just keep changing all the time, right? So now when I say, well, hey guys, I'm sending a light, let's say maybe like I'm putting in maybe like a red light, yellow, red, or whatever. You might say like, Ajahn, that is a red light could have like a 600 nanometer wavelength. Okay, that is the wavelength of the lead light approximately. And then you can calculate the speed of light. Using the speed of light, you can calculate the frequency. It is going to be C over lambda. And you plug in the lambda in there, you can calculate the frequency, right? Here's the key. Which one you want to change when light get into the second medium here? What will happen to this light when it gets into glass? Yeah, very good. That's light always has the same frequency. Okay, here we go. So here we go. What you're seeing over here is this. Think about this. Because light go from air to glass, N has already changed, correct? The question is, what's changed? What's changed? I'm sending in the red light. This is red, red. Let's say if I'm diving, I mean, not so, it's not diveable. Okay, sorry. Let's say if I am stuck inside the glass, should I still see this to be red color? The answer is, yeah, Dan, you're supposed to see red. The red is in, red, the red is in. The red's supposed to be in here too, even though the something has already changed because the index of refraction has already changed, right? And here comes the answer. The things that get fixed all the time is frequency. Frequency will never change. So that means now you understand that what is going to change in here is going to be the lambda. You're going to get the new value of the lambda. Why the frequency will not change? Think about this. Frequency is the actual movement of the source. All right, now we go back 2 lectures ago. So to generate a wave, you need a disturbance, and this disturbance has to come somehow move up and down. You generate, simple harmonic motion, or you move your hands up. It's a real physical movement. So if I say I send in a wave with 1 hertz, so that means in 1 second, I have to move my hands up and down and back. That's my actual movements. That cannot be replaced with anything else. So that means if the wave come with one particular fixed value of the frequency, that means it's an actual movement per second that has to happen. So that's why if I'm talking about the red color here, that has some frequency that come in, it has to have exact same frequency going out because it's an actual fluctuation of the electric field or magnetic field. Does that make sense now? So the only thing that you can adjust, it's the rest of this. So because now we have V equal to F lambda, when V is changed due to N, that looks bad now. Sorry, looks dirty. Because now, yeah, V change because N's change. The only thing that you can get changed is just only this. Okay. All right. Everything just revolve around frequency. Frequency will never change. And that's a good thing is your eyes responds to the frequency of light, not by wavelength. So your rod cell and cone cell, whatever in your receptor in your eyes and retina and everything is just response to the frequency of light. So that's why even though you are stuck inside the glass, lambda has already changed, the wavelength has already changed, but you're still seeing the red light because it's still the frequency from the red light. Cool?
Okay.
Maybe I talk too much now, but no need to clap here. All right, guys, that's it. So I hope that I give you enough, things to get going here. All right, guys, come back to our Snails Law over here. So how to use this one is very simple. You just, collect the informations and try to apply this one. The thing is, once again, just like in reflections, these laws apply at a point. Let's take a look. Okay, so when you have a point, see, there is a light coming in, you measure the incident angle, theta 1, apply Snails law at this point, you can calculate theta 2. You're done. Knowing end of air and end of glass. Okay, same thing. You can go from glass to air, no problem. You measure the incident angle, outgoing angle. You take end of glass, end of air. You're done. All right, but there are only two scenarios that can happen. Coming from air to glass. So you're going from small n to bigger n. So you're going to a bigger value of n. The theta will get smaller. With me, guys? Because Snails law is a product. So when n is big, theta will be small. When n is small, theta will be big. That's always the case. Okay, so going from small n to bigger n, the refracted ray will tend to bend toward the normal. On the other hand, when you try to go from big n to a smaller n, okay, the theta on the refracted ray will be bigger than the incident one. So in this case, the incoming ray will get out away from normal. There are only two cases here. What else can it be? Okay, and the table on the left just lists value of n for some, well-known material there. All right, one thing that your friend just put a note there that's very good there. See, diamond. Because we know diamond is like one of the highest density material in the world. It has a very high index of refraction because, light having a very hard time going through. Okay, cool. And what we're going to use a lot is, of course, water. And as you can see, the vacuum and air is pretty close. So we can approximate end of air to be 1 as well. What else that we can going to be able to use? Maybe cloud glass, just a typical glass, windows 1.5 approximately. Okay. Alrighty. Very good. So let's give it a shot and see how to utilize this one. It's going to be simple, guys. Nothing complicated at all. A ray of light strikes a flat block of glass, given value of n of that block, which is good. Now the thickness of this one is given to be 2 centimeter at the angle of 30 degrees. Don't forget this angle means they say with normal. So that's good. So just do that. So you have an incoming light hitting a block of glass at 30-degree angle. Now trace the light beam through the glass and find the angle of incident and refraction at each surface. All right, this one is just like just quick for fun here. So over here, you can see that now you're starting from n, which is air, n equal to 1. You jump right into the glass, n equal to 1.5. So you're coming from small to bigger value of n. So when you go to a bigger value of n, your theta on the way out is going to be smaller, or what I said, the refracted ray will bend towards the normal line. So let me draw that line there. So what you get over here is you're going to get the frame here. You guys with me so far? Okay. And now you will hit the bottom surface again. You draw another normal line there at the point of contact. See that? I always emphasize on this. Okay. And because your incoming is 30, the outgoing, you can use whatever Snails law. We don't want to calculate at this point. They just want you to trace the curve here, trace the ray here. So the theta of incident in the bottom layer will be theta as well. And because on the way out, you're going back out to n equal to 1. So by symmetry of Snails law equation, it will look exactly the same. So I'll show you what it means. All right. At the point A, here, at point A, what you have here is at A, n air sine 30 equal to n glass sine theta. You guys with me? This is how it works. Just apply it right away. And now if you try at B, n glass sine theta, same theta right there, is going to be equal to n air on the way out. So you go out, and then what you can put in there, they look the same. See? Now you can guess on the way out, the angle is supposed to be 30 again. So no problem. You come out there. You guys with me? So that's the whole trace there. That's what happened. Okay. So Snails law happens at a point of interface. You just apply Snails law there. And then if you go from small to bigger, the refraction will happen to make the light bend toward the normal. If you go backward, you're going from bigger ends to a smaller one, then the refracted ray tend to bend away from the normal. Okay, and then you can say, oh, that on the way out, this is going to be 30 degrees as well. Cool, done.
Okay.
All right, so I think this is easy enough for you to see the whole, scenario that could happen in other problems. Let's give it a shot. Next one, guys. Here. When the rectangular metal tank in the figure is filled to the top with an unknown liquid, observer O with eyes level. So this means it's just like try to look at this one here. Like here. Just see corner of E. So don't forget, eyes just see whatever light hits the retina. So it doesn't really know where the source of light is. And it turns out light coming from the corner of the tank, get the refraction happens at the surface and it's just refracted into his eyes. So that's why he can see the corner of the tank by just level his eyes at the top surface of the water, which is fine. All right. A ray that refracts towards O at the top surface of the liquid as shown. Perfect. If D is given, L is given, what is the index of refraction of the liquid, guys? Want to give it a try?
Okay.
It's not bad. Point of refraction happens here. I just put the green dots right there. Okay. So what I can note right away is the incident. Okay, first, draw a normal line first. See, the interface is just that interface. The water is bottom half. The upper half is going to be air. So your incident angle is going to be this. Let me call it theta 1. What about the outgoing or refracted angle? It's going to be 90 degrees. You guys with me?
Okay.
All right. So let's go for it, guys. Apply Snails law at a point. So let me call this point A then, just like before. So at A, you can start from the bottom in water sine theta 1 equal to, now look at the air, it's going to be in air sine 90. Okay, guys? It's very easy to use. Okay. In water, sorry, it's in liquid. Sorry. It looks blue, so I thought it's water. Sorry, liquid. This is what we want to figure out. Right? I want to know what is the end of the liquid here. Now, sine theta 1 is easy to calculate because sine of theta 1 is just going to be L over the hypotenuse here, which you can calculate from Pythagorean theorem. No big deal. Okay, so sine theta 1 is just opposite over hypotenuse, L squared plus D squared. Cool. So this one is known, not a problem. In air, that we always use 1 for it. Sine 90 is also 1. So plug everything in. So in liquid, it's just going to be 1 over sine theta 1, which is square root L squared plus D squared over L. And the rest you can just plug in the number.
Okay.
Done. Cool. And the nice thing about this one is you just have to double check your result. Make sure that your n value never go below 1. And this is the case. You know that the hypotenuse always larger than just the opposite length anyway. So this number is supposed to be bigger than 1. So you should be good. See, that's easy to use. Yeah, try again. Yeah, this one. All right, we'll keep going. So the light beam shown in the figure makes an angle of 20 degrees with normal line in the oil. Determine the angle theta on top and the theta prime in the bottom. The index of refraction of oil is given to be 1.5. Okay, so this one is good. So let me put this one in oil to be 1.5. Let's apply this Snails law at a point. So let's start from the easiest one, the one that make contact with water and the middle interface there. So let me once again call this point A. So at A, you can start from the upper half to be in oil sine, perfect, 20 degrees already measured with respect to normal. So I can use that 20 degree angle right away, equal to in water underneath, and then you want to figure out the theta prime. So you put sine theta prime there. Because in oil is known 1.5, sine 20, you can punch the calculator. In water is also 1.3. We just saw that. And that you can figure out theta prime. You are done. Okay.
Okay.
Try again with the point on the top there. Let me call point B. And at the contact point there. So at the point of interface, you can start from the top if you like. It's going to be in air, sine of theta, okay, equal to, now you go to the bottom, because from the opposite angle over here, this is supposed to go with 20 degrees as well. No problem, because you have two lines that parallel. So in this case, this is just the opposite angle. So you can say you still have in oil, sine 20. Cool. All right. And in air is always 1. Sine theta, that's what you want to figure out. In oil is given to be 1.5. Sine 20 is already, actually you already figured this out. It's the same here. So theta is supposed to be known, and you are done there.
Okay.
Okay, so I hope you can see that this is how easy it is to utilize Snails law. Just, find a point of interest there that you want to apply Snails law, and just do it. There's only two sides of this interface, the upper one and the lower one. Or it could be left or right. I mean, it doesn't matter, right? But one side and the other. All right, try again. Okay. If you already understood the whole concepts here, now the last step that we want to do is very simple. If you trying to look at the condition where the light coming from the high end to a lower end. So we already know that this scenario will give you the refracted ray that try to bend away from the normal, right? You guys with me here? So look at this. So if I have a source now in the higher end material and try to send the light out into a lower end material, as you can see, if you start flat, this one is no big deal. Point A is no big deal because you have 0 incident angle. Light will just go straight out, 0 refracted angle. But when you start to increase your incident angle, there you go, the outgoing ray will get even bigger, right? Because light bend away from the normal in this case. You increase the incident angle, the outgoing angle will get even bigger. You keep increasing the incident angle, the outgoing angle will get even bigger. So there must be a point where you increase your incident angle until you hit the condition where the outgoing ray is just 90 degree. You guys with me?
Okay.
So at that point, it's like, John, what is going on here? Because the refracted ray seems to go like, on the interface, which usually will never happens, because this is just the sort of like the point where you cross between wave is about to get into the second medium or not. This is critical, right? This is critical that the light will still be able to refract into the second medium or not. That's why we named this critical angle. Very good.
Okay.
So the critical angle is the angle that determines the point where the light will decide not to get into the second medium anymore. What I'm saying, it means if you keep increasing the angle beyond this critical angle, there will be no light in the second medium anymore. But what you have, it's going to be a total reflection back, 100%. Isn't that cool? All right. So the key point is every time that you have a pair of materials, large n and small n, you will always be able to calculate this critical angle between those pairs of materials. And this phenomena happens, like if you look at this figure over here, I think you can imagine if you dive into the pool and then you try to look up, sometimes you cannot see whatever beyond the water, but you will see the reflection of the bottom of the pool back to your eyes, just like this one. That is because you are at the angle that the light that eventually get to your eyes actually come from the bottom of the pool. Does that make sense?
Okay.
Okay, so that's why your surface of the water behave like a mirror, just reflecting the light back to you. This is called total internal reflection.
Okay.
Okay. And the way to figure out this critical angle is simple. You still apply the Snails law at the point of interface anyway. So let's take a look at that point, point E. So what do? Just take n of the medium one, multiply by the sine of theta c, okay with me? And then on the way out, it's going to be n of the second medium, but then you know that the angle that you're going to plug in is going to be 90 degree on the way out. And that's it, guys. This allows you to figure out the critical angle between a pair of materials, and you are done.
Okay.
Okay, cool. So I hope now that's clear out things that you say, what does it mean by total internal reflection? And what does it mean by critical angle? That's it. Give it a shot. I said you use this one every day. The application of this total internal reflection is in the optical fiber. So the way that optical fiber works is you try to use light for communication. And to get that light to travel inside a cable, you want light to be sort of, you keep the light in there. And that's what this is just like a, sort of like a simple diagram just to showcase what it means in there. So that means if you have a fiber, so you can, everyone knows that glass or polymer or plastic has a big N here. So N here is going to be larger than whatever outside. So this is a smaller N. So that's perfect. That meets our condition there that light try to travel from bigger N to a smaller one. So it will have a chance to do the total internal reflection there. So if that is the case, then the light will just keep, total internal, keep doing the total internal reflection inside this cable. All right. Even though in reality, there will be some leakage and everything because not 100% of light will just keep doing the total internal reflections, but things can get, amplified over time. So that means when you send light out, maybe like, 20 kilometers, 100 kilometers, then you have to amplify the signal again because of some loss and everything. You have to redo it. So that's what the fiber is trying to do. But the good thing about this one is the reason that the using the optical fibers can enhance the bandwidth a lot in comparison to using the copper wire is because copper wiring using electricity, right? And it used the electronics charge. So those electrons that's running around in the wire will carry the data. And the bad thing about that one is we're going to study this after the second exam, which is electron just repel each other. They have Coulomb interactions. They don't want to stay close by. So that means you have some limitation to put like a super high density of electron inside a single wire. But unlike light is a wave. And wave, you already saw that they can meet and interfere for a while if they want to, but after that, it just doesn't do anything pretty much. All right. So that's why you can put a lot super dense data compression and whatever in a single cable that is using light as a medium of communication. So that's why one optical fiber can replace like millions of copper wires and all this stuff. All right. And that starts the high bandwidth or high speed internet in the last decade and all this stuff. Yeah. What if we use radio wave to communicate? Will it be better or worse? Okay. So the bad thing about the radio waves, it turns out that the wavelength, it seems to be too, if you talk about wavelength, is too big. So in the radio wave region, the wavelength is still in the range of like sub-millimeter wavelength. So it's not so easy for you to squeeze into an optical fiber. So most of the time in the optical fiber, they still use maybe visible region or maybe up to about infrared and stuff. So it's going to be close to that region, but not in the radio. Okay. So the radio is huge. Actually, if you remember, like Joss or Loy or whatever, you have an FM and AM radios. If you talk about AM, which is the kilohertz, that wavelength is like in meter, guys. It's like radio wave. It's in like a meter wavelength. It's huge. And the wavelength is like, it's like the size of the building. And if you're talking about FM radio, the frequency about, it's like 80 megahertz to maybe 108 megahertz. The wavelength is in the order of, it's still like, I don't know, like sub-millimeter and all this stuff. So it's still huge in comparison to what we can use. So we want like nanometer range to communicate. So you can, it can manipulate, sort of like it can, the material responds well in that region. So that's why glass and plastic or polymer can carry those wavelength much better than in the radio wave region. That's what it is. Yeah, do I answer your questions? Okay. All right.
Okay.
Why don't we use UV? Okay, very good. So it turns out if you use UV, the bad thing is the material that you're going to use is going to be very expensive because most of the materials seem to absorb UV. So that means you cannot sense UV very long. It's going to get absorbed in the material. So think about it. I think you have to start from the material first. So from the material point of view, it turns out it's very good in the visible region. Okay, so this means you can sense light in the visible region a very, very long distance. But once you put UV in there, it's going to get attenuated very quickly. Just like your glasses, for example, plastic that you use in your glasses here, light can get through, right? But if you send in a UV, it will get absorbed quickly, right? It won't get much depth in there. So that's why it's going to be, it's not financially viable to use UV in here, even though, I mean, for other purposes, UV may be better, like in the silicon chip etching and all this stuff, when you do like silicon wafer patterning and everything, using the UV is good because you have a very short wavelength. So you can sort of put a very fine detail into a silicon chip and things like that. So that's kind of application is there for the UV, right? But for the communication, I think for the fiber optics problems, fiber optics communication things, I think visible or somewhere near IR seems to be the good one. Yeah. All right. Very good. So with that, then the application is going to be simple. So let's finalize today's lecture with this, right? So you should be able to calculate the critical angle very easily. So what I'm going to show you, and just to summarize about these topics here, is to find out what is the critical angle for diamond in air and glass in air and compare. Does it sound fun?
Okay.
I don't know if it's fun or not, but let's do it. So you can utilize, because this formula is so simple, but if you don't want to memorize it, you can start from Snails Law all the time. So you say sine theta C, n of the diamond is going to be, if you want to count surrounded by air, so you do n air, and then you do sine 90 degree. Okay, cool. So your theta C is going to be the inverse sine of, turn this into 1. So it's going to be n air over n diamond. And it's going to be inverse sine of 1 over, if you look it up in the table, it's going to be about 2.4. Same thing over here. You now know that the formula will look exactly the same. And all you have to do is just replace n diamond with n glass. And you already saw that in glass, we can use like maybe 1.5, let's say. There. Now you notice something. If you punch the calculator, and I think if I remember this one correctly, it's somewhere around 24 degree for the diamond air. And it's about maybe 43 or 42. I don't remember, but you can check my numbers here. So do you see what it is? So the critical angle for diamond air is so small, while for the glass air is bigger. And this is the reason why diamond is sparkling to your eyes. That's because it's so easy for light, once it gets into the diamond, to be able to get reflected back to you, because it takes up to only 24 degrees for it to reflect. But for the glass, it's have to go all the way out to 42 degrees and beyond for it to get reflections. So that's why diamond is easier for you to get reflection back to your eyes. And if you add diamond cut to it, you know, try to introduce many surfaces for it to even reflect more, and then you start to see that bling bling stuff coming out from the diamond, and that's what it is. All right, so that means if you go somewhere in between glass and diamond, you might see like Swarovski sapphire, for example. The index of refraction is somewhere between glass and diamond. If you go back here, for example, like I think it's somewhere here. Is there any sapphire? Oh, here we go. It could be here. Sapphire is 1.77. So, I mean, it's going to look better than glass, definitely. Okay. But it's not going to be as good as diamond. That's why, all right, it's not as expensive as diamond for sure. Okay. So, let alone with some other things. All right. So, I think I'm going to stop today's lecture right here. And next time, we're going to revise these topics by doing a couple more exercises before we move on to the next subject. Sounds good? All right, guys. Thank you for sticking around. I hope you learned something today. I'll see you guys next week. Yeah. Okay. Bye bye. Take care.